In this video, we'll learn about the convergence of sequences, which is the most important notion in this part of the module. Let me start by just roughly telling you what convergence means for a sequence. It means that the sequence gets closer and closer to a certain number. We say that it converges to a number, which we call the limit of the sequence, if no matter how close you want the sequence to get to this number, you can always do that. The sequence will always get arbitrarily close to that limit. So let me define this more precisely. The definition of convergence is the following. We say that a sequence AN converges, or another word that is used here often is tends to a limit L, which is a real number, if the following things happen. If for all positive epsilon, for all positive numbers epsilon, there exists an index capital N, so this is a natural number, an index capital N, such that AN, a little n, the nth term of the sequence, is closer to L, this limit, than epsilon for all indices little n that come after capital N. Okay? I should probably also point out and make a small adjustment here, is that this index from which we have terms in the sequence which will get closer to L than epsilon could very well depend on epsilon, on our choice of epsilon. Okay, so this is our definition of convergence. So this is a central notion in our module. We say that the sequence AN converges to a limit L if no matter how small of a positive value we choose, there will always be an index after which the terms in the sequence get closer to this limit, this number, than that previously fixed small epsilon. Okay, the notation that we use is to say that the sequence has a limit of capital L is we write that the lim of AN is equal to capital L, and we also indicate that the terms, the indices of the sequence tend to infinity. So we are taking greater and greater indices as we want to get closer and closer to our limit L. Okay, so let me go back to this way of visualizing sequences by plotting them and try to give you an intuitive and visual way of thinking of sequences. So what it means for a sequence to converge, if you think of it visually, is the following. We plot the sequence, and what we find is that there is this number L, capital L, the limit of the sequence, for which no matter how small of an epsilon we choose, there will be this inequality. Now, let's look at this inequality, because this can be rewritten in an equivalent way, in the following way, which might give you a better sense of what it really means. What it means is that AN should be between the numbers capital L minus epsilon and capital L plus epsilon. Now this is probably gives you a clearer picture, because it says that the nth term of the sequence is close to L it differs from L only by maximum of an epsilon distance once we are beyond the capital Nth term. Okay, so what this means is we fix an arbitrarily small epsilon, which means that we look at these numbers of L minus epsilon and L plus epsilon, this neighborhood of L we consider, and what we will find is no matter how small this epsilon we have chosen, the terms in the sequence might jump around and be all over the place, but there will come a point, the capital N index, which we have to find, for which, let's say, the corresponding term is over there, but after which all terms will be in this strip around the limit L within the strip of L minus epsilon to L plus epsilon. Okay, so this is the visual way of looking at limits. Of course, a sequence doesn't necessarily have to converge. So not all sequences converge to some limit. But before we talk about that, let me give you an example. What I would like you to do is to consider the following example. The sequence an defined by having the nth term 1 over n. So this is the sequence that we have seen before. This is the sequence of reciprocals of natural numbers. And I would like you to pause the video and think about this sequence, whether it converges or not to some number as n tends to infinity as we progress along the terms in the sequence. Okay, so pause the video and use the box below to input the limit of this sequence as n tends to infinity. Okay, so I hope you paused it, and I hope you could convince yourself that the limit of this sequence as n tends to infinity of 1 over n is 0. Why is it 0? It is because, intuitively, because we are dividing 1 by a number n that gets greater and greater, so as a result we should get a number that is smaller and smaller, less and less. The way to prove that it is indeed 0, this limit, is to use the definition. I'm not going to prove this very precisely, I just want to give you a sense of proving this. The way this usually works, the way I like to imagine this, is someone comes in and gives me an epsilon, and they don't want to help me in any way. They are going to give me some really small epsilon, so they want to make my life hard by giving me a small epsilon like 0.2 and telling me, okay, now find the index capital N, from after which you will have terms in the sequence that are closer to your limit than that number they have just given you. So, okay, so what I would like you to do is now take this value of 0.2 and try to find the index after which we have this inequality satisfied. So after which an gets closer to L than epsilon for all indices little n greater than capital N. Okay, so again, I want you to pause the video and think about this particular example with epsilon being 0.2. Find this index after which an gets closer to its limit than epsilon. Okay, I hope you paused the video and have considered this example where I have an to be 1 over n, L is suspected to be 0, well, that is our guess for the limit, and epsilon, what is given to us, is 0.2. So if I consider the left-hand side, that's just 1 over L. The right-hand side, the epsilon, is just 0.2, which is also 1/5. So rearranging this inequality by multiplying it with 5n will give me 5 is less than n, or rather n is greater than 5. So it means that this inequality, which is required for in our definition of convergence will be satisfied once n is greater than 5. So this index of capital N shall be chosen to be 5. Okay, I hope you got it right. Now, to continue, as I mentioned, sequences does not have to be convergent. It could also be the case that there is no limit to our sequence. So to continue with the definitions, a sequence AN that has no limit is called divergent. We simply say that if the sequence has no limit, it diverges. It could also happen that the terms in the sequence get greater and greater, and no matter what kind of ceiling you would like to have for this sequence, they always go beyond that certain ceiling, in which case it's not only divergent, it won't have a limit, but it will diverge to what we say plus infinity. So if for all, let's call it capital K bigger than 0, there is an index capital N such that the nth term of the sequence is greater than capital K for all indices that come after capital N, then AN diverges to plus infinity. So this is what we say when a sequence gets gets greater and greater. So we say that it diverges to plus infinity, and there is no upper limit to a sequence. It just grows and grows beyond any ceiling. Okay. Similarly, we can talk about a sequence diverging to negative infinity if no matter how small of a number we pick, a negative number, smaller and smaller, we can always find an index so that the terms coming after that index are less than that previously fixed small number. Okay. Finally, just to finish the video, I would like to show you that if a limit exists to our sequence, then that limit is unique. There is only one limit to a convergent sequence. So this is our proposition. So this is about the uniqueness of the limit. So a sequence AN has at most one limit. Because of course it could have no limit, in which case it's divergent, but if it has a limit, it has only one limit, not two or more. So the proof is going to be indirect. So we are going to prove this statement by contradiction, meaning that we assume that there is, rather that there are numbers L1 and L2 with them being different, so distinct numbers, such that the limit of AN is both L1 and L2. Now, let's see if we can make a few logical steps and arrive at a contradiction, because if we do that, we have shown that there was our initial assumption of having two different limits was wrong. Okay, so what does it mean to have a limit? Well, we just use the definition. So for any for all epsilon greater than 0, all positive epsilon, there are indices n1 and n2 such that, so all I'm doing is I'm using the definition of convergence such that, well, for the first limit, an has to be closer to L1 than epsilon, and for the second limit, this has to happen for all indices that are greater than n1, and similarly for the second limit, an has to be closer to L2 than epsilon for all indices that are greater than n2. Now, what I can do now is to pick a very special value for epsilon. So let epsilon be half the distance between L1 and L2, these two assumed limits. Okay, so epsilon is half the absolute value of L1 minus L2, and little n, our index, should be greater than both of these indices, n1 and n2. The reason we do this, to pick such an index, is to have both of these inequalities be satisfied. So, because if we do that, then what we find is that our epsilon, which remember is just half the distance between these two assumed limits, is equal to, well, this can be rewritten in the following equivalent way. We just take L1, subtract an, then add an. This way we didn't really added anything, so it really is equal to the previous expression. We just have a minus an and a plus an. And then what we'll do is we'll group these terms in such a way, L1 minus an plus an minus L2 in absolute value. And what we can do now is we can apply the triangle inequality, which says that if you take the absolute value of the sum of two numbers, you will get something that is less than or equal to taking the sum of the absolute values of these numbers. So it's less than or equal to a half times L1 minus an in absolute value, which is the same thing as an minus L1 in absolute value, plus an minus L2 in absolute value. So this was multiplied by half. And next, we can now apply these inequalities, because little n is an index for which both capital N1 and capital N2 are less than little n. So we do have these inequalities. So each of these terms are strictly less than epsilon. So this is strictly less than 1/2 times epsilon plus epsilon, which is just epsilon. And look at what we have found. We have, through some logical steps, correct steps, and our initial assumption that there are two limits, we have found a number, this epsilon, that is less than itself. This is a clear contradiction. So no such number exists. This is a contradiction, implying that our initial assumption was wrong. So there are no two limits to a convergent sequence. It can only have one unique limit. Okay, I hope you enjoyed this video, and I'll see you in the next one.